Okay, let's take a look at this, this first kind of example. This is something that we did already, if you guys remember. We're now going to find the area under the curve, but this is also going to include, and I'll put this in our notes, what we know as also net area. And so we're going to take a look at how this works. So I think, to remind you, first of all, you have a lower limit and an upper limit value. These are the lower limits and the upper limits here. The one on top, the larger value, is the upper limit. The one on the bottom is the lower limit. And so you see this as 0 less than or equal to x less than or equal to 4. So that's the interval here. And that's what's represented again by these limits. Now, to remind you that from 0 to 4, in this picture, we start here on the left. This is 1, 2, 3, and 4 down here. And this is 0. The line, and in this case there's 2, goes through 0 and 4 on the x-axis. So what this means is that this is the vertical line x is 0, and this is the vertical line x is 4 here. So we're trying to find the area under the curve between these two vertical lines here. And that's what's meant up here when you say x is 0 and x is 4 by the limits. Okay, if you guys remember some of this. Now, okay, so that's kind of what we're looking for. Now they're saying to compute the area under the curve, well, here's what's going on. I guess let's try to do it this way. Let's see what looks better. They're trying to find this area here. And that kind of looks a little weird, but anyway. Let's try this. This is the area they're looking for. That maybe looks a little bit better. Okay, so they're trying to find this area under that curve. And what they didn't mention, though, which is happening as well, is you also have this x-axis here. Okay, so the x-axis we already talked about, that's the horizontal line, y is 0. So there's some information here that's going on. So I just want to let you guys know they were trying to find this bounded area or this area under the curve. And like I mentioned earlier, keep in mind that we have an approximating rectangle here. That's back when we derived the fundamental theorem of calculus part 2, and we went through the area approximation. So that was kind of what we got our hands on. So this area is going to be positive because that length of that rectangle is positive. Okay, if you guys remember that. So anyway, I just want to go through those details. Now, by the fundamental theorem of calculus part 2, we know that this area is going to be the integral from 0 to 4, or let's write down this fundamental theorem. This is the antiderivative evaluated at b and a, and we're taking that difference. Okay, and I want you to notice something that was very important if you guys remember. Your function f must be what? Continuous over that interval from a to b. And so you guys know the square root function is a nice, beautiful, continuous function for values of x greater than or equal to 0. So we're in business. We can use the fundamental theorem of calculus part 2. So that's what we're going to use. Fundamental theorem of calculus part 2. So what that means for us now will be, we're going to integrate, let's start over here for this area, 0 to 4, the square root of x, dx. So doing the homework this weekend, what do you guys remember? What is that actually going to equal? Or what should we replace this as? Yep, x to the 1/2. Is that right? Okay, good. And so if this is x to the 1/2, that means our area is going to be this integral. And so what do you guys use now? You guys remember? What do you use over here? Yep, you see that function? We're going to use the power rule. So by the power rule now, we get x to the 1/2 plus 1 over 1/2 plus 1. I'm going to draw this line and say x is 0 here and x is 4. Okay, this is our notation that we're going to use here now for these definite integrals. And so what is 1/2 plus 1? Do you guys remember? From all that homework, you should know what this is. This is what? That's x to the 3/2 over 3/2, evaluated at x is 0 and x is 4, which is really 2/3 x to the 3/2. And we evaluate that at x is 0 to x is 4. So this, again, this is my antiderivative right here. This is that big F of x. And then here are my limit values. So the rest of the fundamental theorem of calculus actually says I replace this what? 2/3 with 4 to the 3/2. I subtract and have 2/3 with 0 to the 3/2. Because this portion here, this is my f of 4, and this is my f of 0, and I am subtracting. So we're going to have to now evaluate some of these functions, right? We have to know, are these values here? What are these values? What is 4 to the 3/2? And what's 0 to the 3/2? Okay? So I'll start with the easy one. 0 to the 3/2 we know is what? That's 0. Is that true? Does anybody happen to know what's 4 to the 3/2 though? Don't you need to find the square root of 4 first, which is 2, and then you cube 2? You guys remember this? You guys know what I'm talking about? Okay, let's put it down here so we know. 4 to the 3/2, this is 4 to the 1/2, cube, square root of 4 cubed, is that right? 2 cubed, which is what? So this is 8. So altogether, we have 2/3 times 8 minus 0, or we have simply 16 what? Thirds. So ladies and gentlemen, up here, we found the area under this curve here. That's 16/3. And again, notice that this area is positive here. Okay, because the curve is strictly above the x-axis, meaning every y value is actually positive. It's greater than or equal to 0. If you include that axis anyway. So this is how we use that fundamental theorem of calculus part 2 to find the area under the curve, or what we'll see also as net area. Okay, you guys okay with that? This is a lot of details here. So it's based on whether you did the homework on the indefinite integrals. And so now, you guys have, I'll put this online. You guys will have a copy of it. Now we're going to go to the next question here. Now take a look at this. I don't know. Does that red stand out a little too much, you guys think? I don't know. No, you're okay with that? All right, now let's take a look here. Take a look at the limits. X is from -2 to +3. Is that right? So -2, let's put it over here, less than or equal to x, less than or equal to +3. So we're going to need to find that interval between -2 and +3. And so in this picture, we go to the left, 1, 2, there it is. This is where -2 will be. And in fact, we go all the way up to the curve. And so yes, this is the vertical line, x is -2. And the other, we have 1, 2, and 3. So this is the vertical line, x is 3. So the area under this curve here is going to look something like this. Okay, so we're going to find that area. Now notice something, that the curve's above the x-axis, so your area is going to be what again? Positive, is that right? Okay. Now, is this a continuous function over the interval -2 to 3? Yep. So what does that mean? We could use the what? Fundamental Theorem of Calculus, Part 2. So, to find that area, we have to integrate over the interval. Now, you guys can see, what rule are you going to use here again? Right? You see this function? You use the power rule, is that right? So this is x to the 2 plus 1 over 2 plus 1. We're going to evaluate that x is -2 and x is +3. So doing our arithmetic, let's put our answer up here. We need the space. We get x cubed over 3 from -2 to what? +3. So now we just plug in the values, right? We just need the difference between the antiderivative and the upper limit and the antiderivative and the lower limit. So we get now what? 3 cubed over 3 minus what? Is that a -2 cubed over 3? So it looks like we get 27 over 3, right? Minus a -8 over 3. And so this is going to be 27 plus 8, both over 3. What do you guys get? What's 27 plus 8? 35. Yep. So our answer is going to be 35/3. So we found the area under the curve between -2 and +3. Okay, you guys okay with that? All right, let's take a look at this here. Our limits are between 0 and 4. So we need to draw these vertical lines at x is 0, which happens to be the y-axis, right? And 4, we go 1, 2, 3, and 4. Here's where 4 would be. There you go. So when we sketch this curve, we look at the area under the curve. The curve is already sketched there for us. There's the line y is x. We notice that this curve is above the what? It's above that x-axis, so your area is going to be positive, right? Okay, so is it continuous over the interval? Yep, is your function continuous, right? This function over here? It's continuous, so by the Fundamental Theorem of Calculus, Part 2, we integrate from 0 to 4, x dx. Now remember, the power here for x is 1. So what rule do you guys use again here? What are you guys going to use? Power rule, is that right? 1 plus 1 over 1 plus 1. Evaluate that from 0 to 4. So we end up with, let's go up here, 1/2 x squared, 0 to 4, which becomes, remember, you're going to have to write this as what? F of b minus f of a, which is 1/2 4 squared minus 1/2 0 squared. This portion is 0, is that right? Okay, so what's 1/2 4 squared going to be? Looks like 16 halves, or better known as what? 8. So this area under this curve here is 8. Okay, you guys okay with that? And that's kind of interesting. Oh, here's an interesting question here. Okay. So for this example, it's going to be a bit interesting for us. Right, for this example, let's take a look at the limits here again. The limits here are from -3 to +4. So we write this as -3 less than or equal to x less than or equal to +4 here. So we have to find where -3 is. 1, 2, 3, right here. There's -3. We have to find where +4 is. 1, 2, 3, 4. So we're going to go and draw these vertical lines. And what you guys notice now here is a couple of things here. Okay, so to the right, remember we said we're going to keep this blue, I guess. To the right here, you have area under that curve. And to the left, I think we're going to say, we're going to keep that, what, red, I guess? We said that? Yeah. So notice what I just did here for you guys. On the left, you have negative area. Is that true? Do you guys remember this? We have, again, let's find out if what we can use. Let's use this. You have that approximating rectangle here. You have the approximating rectangle over here. So the rectangle here on the right has a height value that's positive. And then the rectangle on the left has a height value that's what? Negative. Or a length value that's negative on the left, a length value that's positive on the right. So what's going to happen here now is we're talking now net area. Okay, and if you guys notice, it's probably going to be positive. Why would you think it might be positive? Because there's more blue area than what? Red area. Is that right? So you're going to get a positive value. Let's check. Now, is this curve continuous over the interval? Okay, so we can use the fundamental theorem of calculus. So now, let's start doing the work down here. -3 to 4, x dx. We already seen that this is going to be x squared over 2 from x is -3 to x is 4. So we'll have 4 squared over 2 minus -3 squared over 2. Is that true? Did we evaluate this properly? F of 4 minus f of -3, where f is the antiderivative function? Okay. So this is going to give us 16 halves minus 9 halves. Is that true? And what's 16 minus 9, by the way? 7 halves. Good. So notice, is that a positive value? It's positive. So like we seen in the curves that there's more blue area than red. So yes, that's going to be positive. So this is how we find the net area now. Okay, so you have a portion of the curve that's below the x-axis, and all those y values below the x-axis are negative. So you're going to get a negative length height for that approximating rectangle. Good. That's not too bad, is that right? Here's another thing I want to point out to you. Yeah, let's kind of notice something here. Let's put a little detail here. For -3. So we have a problem here, right? You're saying 4 less than or equal to x less than or equal to what? -3. It does. Your limits don't work that way. Okay, but can we integrate this? The answer is yes. Let me show you what's going to happen here first, okay? The function is continuous. If that makes you uncomfortable, maybe we should do it this way. Let's give you guys a fact here. I'll write it up here. The integral from a to b of f of x dx, I can factor out a -1, and I could change my limits here. Let's do that. Let's do it this way. We're going to say b and a. I factor out a -1 now. Did I do that? I'm still doing it backwards. A and b. And then now this is going to be what? A and b fx dx. Now, again, people kind of look at this and say, well, where does that come from? Remember this delta x we found, the width of our approximating rectangle? Remember this width, delta x? That is always going to be the right endpoint value minus the left endpoint value. And that's going to assure that that delta x was positive. If you read it the other way, if you try to make the left minus the right, and you say, okay, let me define delta x to be left minus right, well, that difference is going to be negative. We never actually measure length horizontally that way. It's always the right value minus the left value, and that's going to be an important factor. So we can always factor out a negative and switch the limits, which is what we just did right here. So notice that this is now negative. But we can still use that theorem, but you may feel more comfortable if you want, if you like. You may say, I think I want to use that relationship. And I'm going to write this as what? Negative integral -3 to 4 x dx, if you like. And now this is just like the prior problem. Let's take a look. Is that right? Yeah. But this time you're going to get what? Yeah, it's just like the prior problem. So let's write this down here. So this will be negative, if I write it down here, -1 times that integral, which was 7 over 2. Is that right? So what's your final answer going to be here? -7/2. Now, what happens when we integrate from 4 -3x dx? We get 1/2 x squared, evaluate from x is 4 to x is -3. And again, we have, well, f of -3 minus f of 4, which is 1/2 -3 squared minus 1/2 4 squared, which gives you 9/2 minus 16/2, and then sure enough, this is negative what? 7/2. So what I want to remark here is simply this. If they write your limits this way, where it's backwards, this isn't even true. So you guys know, this is a false statement here. That's a false statement. That's not even true. Let's put that word down in red. This is false, right? We can fix it this way by putting the negative sign. And now we can write a nice interval that includes here from -3 less than or equal to x less than or equal to +4. But here, again, the area is negative because they just switched those values here. But the reason is right up here. Anyway. Okay. Let's look at the next one. I want to kind of give you guys that property here. The next one here, if we notice, our limits now again. -2 to 4. Is that a true statement? Is that how we really write our intervals, from -2 to +4? Okay. So we don't have to switch those limits and put a negative sign. So all is well. So we have to locate where negative 2 is. Here it is. And we draw our vertical line. Notate where positive 4 is. It's over here. 1, 2, 3, and 4. Draw your vertical line. And then the area is above the what? X-axis. So we'll keep that system of being blue. Doesn't matter. Or we could go back to the gray. What do you guys like, the gray or the blue? People are a creature of habit. Area under curve. Okay. So since most of the area is above the what? X-axis, this is going to be positive, right? But you have an issue here. Anybody know what the issue is? How do you integrate the absolute value? So how do we integrate this? So here's going to be something that I'm going to use some of the scratch paper above here so we know here. Okay? Let me give you a tool that you guys want to use for the rest of your life. And I think I'm going to use this in black here. We'll use the scratch paper. This is a piecewise function. The absolute value of any function is defined to be that function when the function is greater than or equal to 0. Or it's opposite that function when that function is less than 0. So we're going to use the piecewise definition of absolute value here. And we're going to see a few of these. So always remember, piecewise is going to be a pretty important thing. So what this means is the absolute value of x equals what? X when x is positive or 0, and it's minus x. Oops, sorry. X has to be greater than or equal to 0. Here, x has to be less than 0. This is the piecewise definition. So you have two pieces, one on the right and one on the left. And to let you know, let's see if you guys remember here. Let's do this purple, maybe green. All right, purple and green. So for the purple, these are positive values of x, or 0. So if you go to the curve, they're talking about what? This portion of that curve. Because those are the x values are positive. You guys okay with that? And so that's the graph, in case you guys didn't notice, that's the graph of y equals x. On the other side, you have that green portion. You use the green portion when x is what? Negative. So negative values of x have the corresponding y values, because this is what these things are. That happens for this portion. And again, that curve here is, so you guys have, is y is negative x. So you break this up into what? Pieces. You have to use piecewise function. So what that means now is, for our integral, define it in pieces. Remember we used that property? I think I gave you guys this property in the past, right? So let's note. You might say the integral from a to b f of x dx was the integral from a to c plus c to b. Remember we did this? I gave you this property here. Okay, where c is in the interval from a to b. And we'll put some open endpoints there. C has to be in that interval. Do you guys remember this property? Let me draw a picture. Should I draw another picture for this? Yeah. Here's the function. Here's A. Here's B. Now we need a C somewhere. Oh, let's put it in red. Here's that C. This is the C they're talking about. Is C in the interval between A and B? Not at the endpoints in the interval. You guys okay with that? So we have two portions here. I'm going to change these colors. How about gold? You have this portion, and then, I don't know, how about pink maybe? You got that portion. So all we did was find the area of each piece separately using a point between A and B. That's the C value. So the gold integral is right there, and the pink integral is over here. Don't forget to always do what? Add. Boy, all the things we have to do to visualize. Look at that. Okay, so what you'll have now for this question is, how does that affect this curve? Here's how we start to write this integral. Okay. We can write it here if you guys like, or we can start writing it up here. What do you want to do? Write it above? So this integral is going to be from -2 to 4, the absolute value of x dx, is, write it in two pieces. What's that endpoint? What's our C endpoint in this problem? You guys know you want to let C be 0 here. You say, why? Well, from -2 up to 0, I have the green piece, which is what? -x. You guys see that there? It's the green piece. That's the left piece. Plus my integral from 0 now to 4. Now, what's the right piece in purple? See this? It's going to be what? X dx. That's the purple piece. So you're going to actually use the piecewise definition function, the definition of piecewise function, write it as a piecewise function, and now you can apply your what? Your power rule and your properties. Okay, you guys okay with that? Now you can find the antiderivatives now. So this gives you like, maybe you want to think of it as, there we go, my first integral and my second integral. Is that right? So the first integral is going to be in green. So let's write down that green integral. Here's I1. Now, if you like, I guess we could do it down here. Let's try to fit this in. It'll work. What's your first integral again? I1? It's going to be from -2 to 0 minus x dx. By properties, I can pull out that negative sign. Is that true? And now, what do? Don't forget there's a negative sign. Apply your power rule. Isn't that x squared over 2? Evaluate that from x is -2 to x is 0. All right, you guys okay with that? And so up here, let's put this f of 0 minus f of -2 becomes -0 squared over 2 minus a -2 squared over 2. Be very careful with your arithmetic, because you have here subtraction here. This is a difference. So sometimes you have these negative signs, you got to be super careful. Now this first portion here, you guys know this is always going to be 0. Is that right? So you have negative, let's see what this is. This is a negative. Did I make a mistake? Nope. -4 over what? 2. And this is -2. What's the opposite of a -2? It's a +2. Now, that means this portion over here is what? That's 2. Is that right? The area under that curve on the left is positive. Now, that makes sense because it's above the x-axis, right? Okay, good. Now, let me point out something, because you see all these negative signs, and that's going to be a little bit weird for people. don't forget from the beginning you had that negative sign. This is from your antiderivative function. Okay, you guys okay with that? So that negative sign is still here. Oops, undo that. That negative sign is right there in green. It's also right here because that's your antiderivative function. So I have those two negative signs. That red difference is always there, okay, because you're taking the difference. It just so happens that the number also is a -2. That's negative as well. So you got these negatives, so just be very careful. This is here, down here, the antiderivative function. It just says it's going to be negative. It's -1/2 x squared. Now, let's find, in purple, let's find this second integral. You say, which integral is that? This is going to be this integral right here. From 0 to 4, x dx. So I2 is 0 to 4 x dx. Power rule. X squared over 2, x is 0, x is 4. My antiderivative is not negative. It doesn't have a negative sign. So we're going to write this now as f of 4 minus f of 0, which is 4 squared over 2 minus 0 squared over 2. Remember, you have a difference there. So 4 squared is 16, is that right? We got 16 over 2 here. And let me remind you that 0 squared over 2, that's 0, so that's gone. What's 16 divided by 2, though? This is 8. Now, that should make some sense because of the fact that over here now, that's positive. It's not a negative sign. Let's be careful here. I want to be careful because people might look at that and go, oh, is that a negative sign? No. This portion is 8 for the area. Let's go back here. This portion in green was what? 2. So you have 2, you have 8. What are we supposed to do with those numbers now? Yeah, go back here. We're supposed to what? Add those. So the final answer is going to be 2 plus 8, which gives you what? 10. So this equals 10, ladies and gentlemen. So this is how you handle every absolute value function. You have to handle it by the piecewise definition. Okay, there's no rule integrating absolute value. Is that right? So I want to show you guys these fundamentals here, what you're doing. Then you say, oh, here we go. What about this one? Well, take a look. Is the orientation of our limits okay? Is that from -3 to what? +3? Excuse me. You guys okay with that? Yeah. So, x is -3. X is +3. And notice again, the area under the curve here, it's going to be positive, right? Because these values are above the x-axis. So, okay, here's a couple of things you guys can notice here. We can go through the piecewise definition again and remind you, let's continue. This is on the left, right? And this is on the what? Right. So we can write this as two integrals again. We can integrate from -3 to 0, -x dx, plus 0 to 3, +x dx. I get my two integrals like I did before. And I guess in green here, we notice that if we integrate this particular integral, call it I1. I don't think that's the same green. You call it I1, and that's minus integral negative 3 to 0 x dx, which should give us negative x squared over 2 from x is negative 3, x is 0. We write this as f of 0 minus f of negative 3, which is negative 0 squared over 2 minus negative 3 squared over 2. Now let's be careful. That subtraction's there. Our antiderivative is negative, so that sign is there. And that means our function value of negative 3 is in the proper position as well. So everything's okay. All right, well, this first portion is 0. So I get negative 9/2, which is opposite of a negative is a what? Positive. So this portion here is 9/2. Okay, in purple, I2 is the integral from 0 to 3, x dx, 1/2 x squared, x is 0, x is 3, 1/2 3 squared minus 1/2 0 squared, which will be 9/2 again. Don't forget that. This portion is 0. So on the right side, let's undo that. 9/2 as well. So, okay, 9/2 and 9/2, what does that equal? If we have to add these, right? So your final answer is going to be here. We have what? 9/2 plus 9/2, which is, what does that equal? 18/2, better known as what? 9. So the area under the curve here over a symmetric interval. What do you think we mean by being symmetric? We have what's called a symmetric interval. -3 to +3. So we have a symmetric interval. We also have, I'm going to point this out to you guys. Why did I draw that or highlight this area, the y-axis? Does anybody happen to know why? You have a very special kind of function here. This is a function that has this special property over a symmetric interval. You might say, what are you talking about? Okay, here's what I want to give you guys. If you have a function over a symmetric interval, this happens only if your function f is an even function. And of course, it's continuous over the interval, right? So the function is even, and let's just emphasize continuous over the interval as well. It's assumed if you're going to take the integral. But the point is, your function has to be what? Even. What's nice about even functions? Even functions are what? Symmetric. Symmetric about what? The y-axis. What you can do then is integrate from 0 to a. This will save you some time. And just do what? What did I just do? I'm only doing one integral. I'm doing the one on the right. And what's the deal? I have to do what here? Let me put it in red. Double my answer. So this property that I just gave you guys here is a very important property. Okay, it saves you time for some questions. And let's remember, what's your definition here of a function being even? Right? We say f is even if f of minus x equals what? F of x. So even functions are very important for us. What are the most popular even functions again? X squared, x to the fourth, x to the sixth, x to the eighth, pretty much every even power, okay? Do we have any trig functions that are even? Which trig functions are symmetric about the y-axis? Well, sine's not. Sine is symmetric about the origin. Cosine is what? Is a nice even function. Is tangent even? Nope, it's odd. What's the reciprocal of cosine? Secant. Secant is also a nice even function. So just to remind you guys here from your past, the reason you care about even functions, in terms of integrals, you must have a symmetric interval. Now you say, what's a symmetric interval? We write it this way, two ways. From negative a to a, or we say negative a less than or equal to x, less than or equal to positive a. This here is your symmetric interval. So double check. Isn't it true if we just got the area on the right, you say 9 halves right here, and I doubled 9 halves, what do you get when you double 9 halves? Right? What's 2 times 9 halves? Isn't that 9? Isn't that the same answer? So to let you guys know, absolutely, you can use this fact, and it saves you a lot of time in your life. You'll learn to love it. Okay? You guys will learn to love it. So this is why I went through these very simple examples of definite integrals to go over a lot of these little details that will pop up. Okay, you guys okay with that one? Pretty good. All right, here's another kind of simple integral to remind you guys here. Here, what do you guys know about the function here? It's a constant function. We're still integrating from negative 2 up to 5. So that's true. This is how we write our interval, smallest to largest. And yes, you might notice you have a constant function. So f of x equals what? That's 5. So when we notate again where negative 2 would be, that's to the left over here. And positive 5 is to the right here. Right, that's x is 5. 4. I apologize. Thank you. Okay. There we go. And what do you guys see here? What is this? Anybody want to tell me what this is? This is what? Isn't that a rectangle? So, I mean, if you know the geometry, can't I just multiply the length and the width? Right? You guys know what I'm talking about? So notice, here's your area, just so you guys know. Here's my length and my width. What's the length of this? And what's the width? Well, 5 minus the negative 2 times 5. 5 plus 2 times 5. 7 times 5. I know the area already. It's 35. I can use geometry. 4. I still got that. Yeah, I still got that number in my head. Okay. 4. What's 7 times 4? So this whole area is 28. Okay, let's use calculus though. It's a nice continuous curve over the what? Over the interval.
Is it 4?
Did I make a 4? Ah. Okay, let's go back here. There we go. Oh, let's drink some more coffee here. That's 6 times 4, which is now really what? 24. Let me double check. Hold on. And this portion's 5. Oh, that's where we made the mistake. Okay, good. We really have to drink this coffee here. All right, let's start over here. Okay. Try to show off here doing some geometry. All right. Constant function still 5. Now, all right, let's go through some detail maybe. Do you guys know how to get this length down here? Yeah, what is that? Yeah, you guys are okay with that, right? 4 minus a negative 2. 4 plus 2 is what? 6. 6 times 5, because this dimension here, if you guys want to find this dimension, right, your width is 5. So the area here will be 6 times 5, which gives you what? Right, is that 30? Okay. 6 times 5. So just so we know that area. A couple of things here. If we remember the calculus, negative 2 to 4, function is 5. Okay. Pull out your what? Constant. Remember this? And what's the antiderivative now if I go up here? What's the antiderivative of 1? That was x. Evaluate this from negative 2 to positive 4. So you got 5. Don't forget to, if you need to, write your f of 4 minus f of negative 2. So you're going to have 5 times 4 minus 5 times a negative 2. And 5 times 4 is going to be what? 20 minus a negative 10, or 20 plus 10, sure enough, gives us what? 30. So we can use calculus, we can use geometry, ladies and gentlemen. And I want to give you guys maybe another fact here. Here's a fact in terms of calculus. The integral from a to b of a constant times, or just a constant function. So it's a constant times dx, though. Well, we can pull out the constant, as you guys know. And then this integral here is just what? That's just x. So we get c times x from a to b f of b minus f of a will give you what? cb minus ca. Factor your c out. Here's what you guys have. So if I want to integrate from a to b a constant dx, it's c, the difference of my limits. That's what we just did. And that happens when your function's just a constant. Okay, so here's another property that you guys want to use. Anyway, oh, here we go. Same thing. But let's notice something here. 4, oops. Let's write this down. 4, negative 2. The lower limit is 4. That's not true. Is that right? You guys okay with that? Isn't your lower limit supposed to be smaller than the upper limit? You guys notice this? All right, let's put some properties together here. What do? This is minus the integral of negative 2 to 4, keep that 5 dx. Notice what I did of the negative sign, is that right? And what did I do with the limits? Switch the limits. Let's double check now. Isn't negative 2 less than or equal to x, which is less than or equal to 4? Okay, we wrote the lower limit as a lower limit value or a smaller value and the upper limit as a larger value. So we can still do this. And then, what do you guys get here? Let's go further. This will be, if you want, pull out your what? Constant. Negative 2, 4 dx. Is that right? Or you can say, Mr. Judge, can I keep that constant and use the fact you just gave me? Write down the constant and then take the difference of my what? What do I take? I take the difference of the limits. I'm using the prior fact, right? I'm using this, where here's my constant. It happens to be negative. And then I'm going to take the difference of these what? Of B and A. Here's a difference. Here's B and A. And then my constant happened to be what? Negative. So let's see what we get. We get what? Negative 5 times 4 minus a minus. Isn't that 4 plus 2? Negative 5 times 6. What does that give you? That gives you negative 30. So let's be careful here. I want to really emphasize this. Even though they gave you the question this way, you integrate 5 over this interval that's not a valid really interval being smaller. I mean, we could write it that way, but the real function is going to be negative 5. Okay, you guys okay with this? So it's really a negative 5 function, not a positive 5 function. So you might say, well, where's negative 5? It's below the x-axis. This is why your area is what? Negative. It's because of the limits they originally gave us. It just switches that constant value from a positive to a negative. And so now, it makes some sense in case you guys wanted to see it that way. Because your delta x now is negative versus positive. So that's really what's happening there. So I want to point out that important detail. So we're using all the properties. Everybody okay with that? Yeah. So now we get to have more fun because let's look at our interval here. 0 to what? Pi. Does that make sense to have the smaller value on the left, the larger value on the right? I think we're good. Okay, so 0 to pi. Do you guys know what's the approximate value of pi? 3.14? Well, you guys know the sine curve. Doesn't this happen where an x here is pi? Isn't that where pi is? Right there, is that right? And what about 0? You guys know where 0 is? Right here. This is x is 0 here. It's the y-axis. So they want area under this curve here. This is what they're talking about. Okay, you guys okay with that? So it looks like we're pretty good here, ready to go. So we're going to integrate 0 to pi sine dx. What's the antiderivative of sine? Right? We had a whole weekend of antiderivatives. Thank you. Good, this is the antiderivative function, right? And so we have to have f of pi minus f of 0. So that means minus cosine pi minus a minus cosine of 0. Let's be careful here. Fundamental theorem of calculus says take the difference. So you're taking that difference. Is that true? And what do you guys know about this antiderivative? It's negative. So that negative sign is there. So it looks like we're okay. Is that right? Like I said, you have to be careful. If your antiderivative is negative, you got to be very careful there. So you really have minus cosine of what? Pi plus cosine of 0. And we have to know the values of cosine and the value of, the different values of cosine. Does anybody know what cosine 0 is? I just go back and look at this. Start drawing my cosine curve. Is this going to be 1? Now, what's cosine of pi? What's cosine of pi? Does anybody know if you start drawing that cosine curve? I think it's -1, right? So cosine goes like this. Is that true? You guys know what I'm talking about? Then back up here. Oops. Oops, here's where 1 is. Okay. So the cosine of pi is going to be what? -1. Good. So you have a minus 1 plus 1, which is 1 plus 1. So this value is what? 2. So I want to emphasize here that the area under that curve there is what? Is 2. Okay, pretty good. Now, look what they gave us here. Anybody know? What did they give us? Yeah, if we look at the limits here, it is symmetric. Okay, negative pi to pi, that's good. Yeah, the problem is your function's not even. F is odd. This is an odd function, so let's put that down here. It's not an even function, it's odd. Now, here's the issue, though. If we look at the details, right, they want us to integrate between negative pi and positive pi. So we already know here, this is where our pi value is going to be. Right, x is pi. X is minus pi. Now, earlier we agreed we're going to put the positive area in blue. Or area above the x-axis in blue, area below the x-axis in what? In red. What did we just find earlier, though? This area was 2. Now, what do you think this other area is going to be? This is going to be -2. Now, you may not believe me, but let me do that integral from what? From negative pi to 0, sine. And what's the antiderivative of sine again? Is that minus cosine? So we got minus cosine from x is negative pi, x is 0, f is 0 minus f of negative pi, which is minus cosine 0 minus cosine of negative pi. So I'm being careful. Remember, cosine of 0 is 1, so that's a -1, because this is -1 times cosine of 0. Minus and minus makes that a plus. Plus cosine of minus pi. Now, what's cosine of minus pi? Anybody remember? Is that negative 1? What's negative 1 plus negative 1? Negative 2. Sure enough, it is negative 2. So your final answer is going to be, I take that area in red, negative 2. I add the area in blue, positive 2. What does that give me as a net area? This area is 0, ladies and gentlemen. So this is going to be a very important detail for us. That area is actually 0. And so let's consider this fact. Yeah, question.
Every odd function we have to do it as piecewise?
No, do we do every odd function as piecewise? No. Every absolute value function as piecewise. So we didn't actually use piecewise here. What I could do, let me show you here. I'm just using a couple of tools here for you. You can simply say, okay, Mr. Judge, let me do this question right here. I have a nice continuous what? Function, right? Here's a nice continuous function over negative pi, positive pi. Fundamental Theorem of Calculus Part 2, what does it say? I can do what? I can integrate. Is that right? In other words, I need the antiderivative. Cosine. X is minus pi. X is pi. You guys okay with that? This is minus cosine of pi minus cosine of what? Negative pi. Be careful, because we write this as f of what? Pi minus f of negative pi. Remember this? That negative sign is there. Just so happens your antiderivative is what? Is negative. That negative sign is here, in here, and there. So you're careful. Is that right? And yes, you have a negative pi as well. So this is minus cosine of pi plus cosine minus pi. Now, you know cosine is even. Is that true? So I could do a couple of things since cosine is even. Isn't that cosine of pi? Because cosine's even? I'll get minus cosine of pi plus cosine of pi. What do you end up with here? You get 0 here, ladies and gentlemen. So even if you went from the beginning and you said, okay, Mr. Judge, I'm going to start by just integrating, could you do that? Yes. Did you have to do it with piecewise? No. You didn't have to do it in pieces. Now, you might say to me, then why did you approach this in pieces? Well, because, go back, didn't we already find this in the prior example too? I want to show people that on the other side, this is negative 2, and that when you add, it gets to be 0. I also want to show people a very special property here as well. Because what do you guys notice about the interval? Isn't it symmetric? Yeah. We got a symmetric interval with what kind of function? With an odd function. So odd functions are symmetric about the origin. You might say, what does that mean to be symmetric about the origin? It's symmetric about both the x-axis and the y-axis. So let's give you a fact. Like you had for the even functions. Let's write this down. Here's your fact. If you have a symmetric interval again, and this function f is an odd function over a symmetric interval, what should I write down as your answer? 0. Good. This happens when you have a what? You have to have an odd function. So your function has to be odd, and you have to have that symmetric interval. Right? So let me point out, this is what we mean by the symmetric interval, odd function. So does that save you guys some time? The answer is yes. Let's go back to the definition of an odd function, though. Definition. F is an odd function. When do we know that's an odd function? If f of minus x is minus what? F of x. So this is how we define an odd function again. What are the most popular odd functions? Like, really, x is odd, x cubed, x to the 5th power, x to the 7th power. Functions that look like that or involve those powers, right? What about the trig functions? Which ones were odd? Sine was odd. What else? Tangent is odd. Good. And then what about the reciprocals of those? Right? You also have what? Cosecant and what? Cotangent. So this is another fact that can save you some time. If you notice the symmetric interval, and the function's odd, well, the integral is going to be 0. So stop and think about this. Is every function that you guys see in your life, could you say every function is going to be even? No. Is every function going to be odd? No. Is every interval you're given going to be symmetric? No. So you can't use this if the interval is not symmetric. You can't use the even and odd business when you have a non-symmetric interval, only when the interval is symmetric. So I did want to point out that detail to you guys. Take a look. I wanted to piece it together. You don't have to do this piecewise. You could just find the antiderivative and use the fundamental theorem of calculus part 2. But when you have absolute values, yes, you do have to use piecewise. There's no other choice there. Okay, you guys okay with that? And this is how we evaluate these. Take a look. This is what I'm saying. Look at this one. You do know that your function here is what? But what about your interval? 0 to what? Is that symmetric? No. So what you would do here for this is you go about this integration and say, okay, you got to integrate from 0 to 2 pi sine dx. Well, that's minus cosine what? X. From x is 0, x is 2 pi, which will be, remember this, f of 2 pi minus f of 0. Let's go back up here, which is minus cosine 2 pi minus cosine of what? 0. Be sure your signs are okay. Because again, oops, see what I'm saying? We have to put a what? A minus sign. This is my point. There's a negative. There's a negative. You got to have a negative. Negative cosine 2 pi plus cosine 0. And then sometimes people, I don't think I want to write it backwards, but sometimes people do. You know, sometimes people, if you look in some books, the back of the book, you say, oh, cosine 0 minus cosine what? They just rewrote this where the positive term is in front. That's all. Yes? Is it minus 2 pi? No, it's positive 2 pi, right? Positive 2 pi right here. And anyway, what's cosine of 0, by the way? 1 minus, what's cosine of 2 pi? Is that also 1? Double check. Is that difference 0?
Yeah.
Okay, let's make sure. That x is 0. Where's 2 pi? It's over here, right? So let's see, what's the blue area? What's the red area? We're already seen from a prior problem. This is 2. That'll be negative 2, so sure enough, that happens as well. So you had 0 naturally, even though the interval wasn't symmetric. That came out to be 0, but you're finding net area. That happens sometimes. Okay, I want to point out, though, this is not a symmetric interval, so don't just think that anytime you integrate cosine or sine, it's going to be 0. Okay, good. Absolute value. Oh, this is a nice tricky one. You see, the prior question, if we notice here, our interval here is 0 and 2 pi. So we've got 0 less than or equal to x less than or equal to 2 pi. Here's where 0 is. Here's where 2 pi is. Notice something here. From 0 to pi, we're above the x-axis. And from pi, let's write this down. This is where pi is. So from 0 to pi, we're above the x-axis. From pi to 2 pi, we're also above the x-axis. Okay, you guys okay with this? Now, what did we see from prior questions? 2. 2. My answer is going to be what? 4. But you might say to me, okay, Mr. Judge, however, we have this absolute value of sine. How does that work? Okay, let me write up here, I guess. The absolute value of sine, well, there's an absolute value. Is that true? Well, that sine, when your sine curve is greater than or equal to 0, its opposite when sine is what? Less than 0. Now, don't forget, we're considering the interval from 0 to what? 2 pi. So that makes this a bit easier. So my absolute value, here's sine. Where is sine going to be? Let's look at this here. Let's see positive here, right? Where is sine positive? Greater than or equal to 0. So if I go back to the sine curve, the prior question, isn't sine positive from what? From 0 to pi? So this portion is going to be what? 0 less than or equal to x less than or equal to pi. Where is that sine curve negative? Yeah, it's from what? It's right over here. From pi to 2 pi. Is that right? And so this is positive, this is negative, pi to 2 pi. And let's be careful here. It has to be strictly less than. And if you want, let's write this minus sign. And this one we could put as sine. So yeah, we're going to have to really emphasize or consider whenever you have the absolute value, you got to use this what? Piecewise. All right, you guys okay with that? So the area here is going to be, if I look at this, we're going to integrate 0, 2 pi. Absolute value of sine will be 0 to pi sine dx plus pi to what? 2 pi. And this is going to be what function? Negative sine dx. Because, Let's color coordinate this stuff. 0 to pi, there's the function. But from pi to 2 pi, here's my function. Okay? All right. So we can think of this as our first integral, and this is our what? Second integral. So zero to, what do we say, pi? Sine, we know is minus cosine. X is 0, x is pi. F of pi minus f of 0. Minus cosine pi minus a minus cosine 0. Double check. The difference is there. Here's my difference. Got that negative sign there. Okay. What's cosine pi again? Negative 1. What's cosine 0? That negative sign is already there, negative 1. What's cosine 0 again? Is that 1? So you got positive 1 plus 1, sure enough, is what? 2. Green, let's do the same. Pi, 2 pi, sine minus cosine, evaluate this from x is pi. X is 2 pi, which is minus cosine. Let's do all the same procedures. F of 2 pi minus f of pi, which will give you minus cosine of 2 pi minus cosine of your pi. I can simplify a little bit. Because let's double check. We do have that subtraction. The antiderivative function right here is negative. Has that appropriate sign there, so we have to check that. Okay. What's that?
Wasn't it, we're looking for the antiderivative of negative sign, aren't we?
No, the antiderivative is, no, this is, oh, good, thank you. Thank you so much, good job. See what happens? Not even awake. Negative sign, good. That makes this now what? Positive, good. Positive. Positive, is that right? So we got positive, and then this will be negative. Good job, I'm glad you're awake. So we got cosine 2 pi minus cosine of what? Pi. That's going to change our answer. Absolutely. All right, what's cosine 2 pi? 1 minus, what's cosine minus pi? Isn't that negative 1? 1 plus 1, which is what? 2. So as you can see, we did find that this portion was 2 here in green, right? We found that 2, and in purple, we found that to be 2, and then 2 plus 2 is going to give us what? 4, like we said. So we can say 2 plus 2 will give you a nice what? 4, like we knew it would be. So I'm showing you a lot of these properties here of integration with some very fundamental curves. And, you know, if you ever have the absolute value, sometimes they put that in there. Just look at it as piecewise. And then you might say, Mr. Judge, what if I notice I have a what kind of function here? Right, see this? 1, negative 1. Symmetric interval. Over an odd. What if you forget? What does the graph look like? And that x is 1 and x is what? Negative 1. So I know I have this portion here in red and this portion here in blue. Let me emphasize this. Right? What's that area going to be? Can I use my fact if it saves me some time? Yeah. This is 0. Okay, because if you guys recall, since f of x is x cubed, f of minus x is minus x cubed, which is minus x times minus x times minus x, which is going to be minus x what? Cubed. Well, that's minus f of x. So in other words, f of minus x is opposite of f of x. That means f is what? Odd. So you use the fact that we have a nice odd function over your symmetric interval, because that interval is going to be between what? Negative 1 and positive 1. So you could use that fact. That's why I gave it to you guys. Nice. Go look at that one again. What do you guys see? Think. Do you have to go through the antiderivative? No. Yes.
On the test,
What's that?
on the test, you have to like do.
Well, you got to do some work. I mean, there's not much work you can do here. I think you want to justify your answer. You want to say at least the function's odd over a symmetric interval. And then put 0. That way we know that you're not looking at your neighbor's paper. Or you're not using a calculator. Because sometimes what people are starting to do is like, I'm not going to do any homework, Mr. Judge. I'm just going to use my TI. I can program how to integrate and do all that. You know, we live in that kind of day and age. So you can, and I'll put on your stuff, show work for credit. So that way if there's just answers, I have the right now to give you a 0. So, yeah, at least state, if you know this is odd, you could say, the function is odd. You don't have to prove it's odd. And over a symmetric interval, and then you could use the fact, and you got 0 there. Yeah. But, you know, you should be rewarded for knowing facts and these details. You see what I'm saying? That's always a nice thing. Okay. What is this? Should we be rewarded? Let's double check. Negative 1 to 1. My function is what? Even. Now you might say, well, what do I do here? You know what I'm going to do? And look at the interval. Negative 1 less than or equal to x less than or equal to positive 1. Here's what I'm going to do. I'm going to say this is going to equal twice the integral from 0 to 1, x to the 4th dx. Now, you might say to me, you know, is this piecewise? Not at all. It's taking advantage of evaluating an antiderivative at 0. You see, this 0 here, ladies and gentlemen, this makes your computation a lot easier. Okay? Your computation's easier when that endpoint is 0. So, we know then, by the fundamental theorem of calculus part 2, since our function is continuous over the interval, find the antiderivative. It's x to the 5th over the 5th power. X is 0, x is 1. This will now give us 2/5 x to the 5th, right? Let's go back and do every detail when you first learn this. 2/5, 1 to the 5th power minus 2/5, 0 to the 5th power. This portion is 0. So we end up with what? 2/5. So even though we didn't go through that detail, x is negative 1, right? The area under that curve here is right here. It's positive, right? That's positive 2/5. Now, did that help me knowing some knowledge? What do you guys think? Knowing that the function was even over a symmetric interval? That was very helpful. Because over here, this integral here, like I said, this portion, evaluating the antiderivative at 0 is a very nice thing that enables my calculations to be Very trivial. Okay, let's take a look at this function here. Here's where negative 2 is. Right? Because I have negative 2 less than x less than or equal to what? 4. X is negative 2. X is 4. We're finding area under the curve here. Okay. So I have to integrate from negative 2 to 4, x to the 2/3 dx. I got to find the antiderivative, right? So isn't this x to the 2/3 plus 1 over 2/3 plus 1? X is negative 2 and x is 4. So I have to know what's 2/3 plus 1, and that'll be 3/3, right? This will be 3/3. So what do you guys end up getting? Is that 5/3? X to the 5/3 over 5/3. From x is negative 2 to x is 4. Now remember this. You write this as a reciprocal, is that right? Remember this portion here? 5/3? This will be 3/5. X to the 5/3. X is negative 2, and x is 4. That's f of 4 minus f of negative 2. So we have 3/5, 4 to the 5/3, minus 3/5, negative 2 to the what? 5/3. So we're going to have to look at some details here. We could do a couple of things here. Okay, let me focus on this here. You see 4 to the 5/3 and negative 2 to the 5/3? How are we going to write this? First of all, notice you could take cube roots of negatives, right? They're defined. So how did we write these things? You guys remember? I think I did some in your homework here. Let me show you what I mean by that. Let's write this down. 3/5, 4 to the 5/3, minus 3/5, negative 2 to the 5/3. We can write this here. Let's use this idea. Did I show you guys about mixed numbers? See your 5/3? You see this 5/3? How can we write that as a mixed number? Right, let's note. What's 5/3 as a mixed number? Isn't that 1 2/3? Is that true? Which is really, by the way, 1 plus what? 2/3. So I can replace this with 1 plus 2/3. 1 plus 2/3. Now, you might say, here's another note. Why do I care? Because I can write x to the 5/3 as x to the 1 plus 2/3, which is x to the first power times x to the 2/3, which is x times the cube root of what? X squared. You see, this is a way that we can actually simplify our radicals. Okay, these radicals are simplified from a 5/3. If you went back to intermediate algebra and you said, okay, x to the 5/3, right, is going to be the cube root of what? X to the 5th power. They're going to say simplify that radical because your power here is bigger than the index, and you can't have that. You have to have the reverse. So this has to be simplified. And so what you can do now is use this relationship I just showed you guys. So that 4 now, you have still the 3/5 here. That's going to be 4 times the cube root of 16. Is that true? Because 4 squared is 16. Minus 3/5 times, you're going to see now what? Negative 2 times the cube root of what? It's negative 2 squared, but that's 4. Is that a little too fast? You want to see every detail? Okay, let's go back here. All right. Okay, I'm going to use this here. This is what we're using. 4 cube root of 4 squared minus 3/5 times negative 2 cube root of negative 2 squared. 3/5 times 4, this has to be a cube root of 16 plus, I'm going to put 3/5 times 2 because minus the minus, cube root of what? 4. So there's a couple of things I think that you can do. You can factor this out, but I don't think it helps much. So let's just multiply. You got 12/5 cube root of 16 plus 6/5 cube root of 4. So when you're looking back at the book for the area, as you guys can see here, it is positive, and the whole area here is found this way. So there's going to be some arithmetic, some algebra, and that's what I wanted to demonstrate to you guys here. So double check here. Do we have everything okay? Does that look okay to you guys? Because, you know, not being awake and then that coffee doesn't kick in and, you know, old age and, you know, dementia, I guess. I don't wake up till noon, or actually wake up till after the class. Anyway. So you guys don't realize all these years I've been teaching calculus in my sleep. What about this? How about this one? X is 0. What's pi over 2? Do you guys know what that is? That's over where? Is that over here? Right? That's x is pi over 2. Yeah, it's a small area right here. All right, I guess we just want to find some antiderivatives here. 0, pi over 2, cosine. What's the antiderivative of cosine? Just going to keep you guys honest. Sine. So as you guys can see, was I kidding about the homework this weekend? Work on the antiderivatives. Sine pi over 2 minus sine of what? 0. I know sine of 0 is 0. What's sine of 90 degrees? Isn't that 1? So this would be 1 minus 0, which is what? This area is 1. Let's look at our intervals here. Negative pi to pi. Okay, so let's see what this area is going to be. Negative pi to pi. So we got, negative pi is over here. And pi is over here. We're finding this area here. What do I know about cosine? Cosine's even, is that right? I got a nice even function over a symmetric interval. What does that mean? Can I use my fact? What does that mean? Does that mean my area is twice from 2 to pi cosine dx? Don't I just find this area here and double it? The answer is yes. Let's double that. Okay. So, the antiderivative of cosine, isn't that sine? Yes. X is 0. X is pi. So, this will be 2 sine pi minus 2 sine 0. Okay. What's sine of pi? Is that 0? What's sine of 0? Was that 0 as well? Ah, I know what we did. We did something wrong. Go back. Yeah, this is not, this is going to be what? Minus pi. So double check. Do you guys see why it's actually important to have the graph even, right? So this is not 0 here. So what is this? You guys know what this is? This is going to be, this first portion is 0, so it's minus 2. What's sine of minus pi? Do you guys know? Isn't that going to be...
Should be minus pi to 0.
Well, we did pi to 0. Didn't we do pi to 0 here? Ah. Okay, and that's pi over 2. Ah, we did this wrong here. Let's go back here. Okay, let's go back. That's probably helpful. Let's go back here. Where's pi at?
In the middle.
Pi is over here. That's where the problem is. And pi is over, negative pi is on the other side here. Okay. So, if we say, what's this area here? Now let's go back with what we agreed in blue. Positive, right? Red. That net area is going to be 0. Is that right? Okay, now it makes some sense. So let's go back and let me remind you, we could do a couple of things. Negative 2 times, what's sine of minus pi again? Is that 0? Which is 0. Sure enough, that's 0. So that's kind of what you're looking at here for this integral. All right, so let's start off on a positive note here. So we're going to notice from 1 to 4. Okay, and so we have to find that area under this curve here. This is what they're talking about. And maybe we have to get a little smaller here for this area. Okay. All right, so hopefully you guys can see that. Maybe we have to do it darker. Maybe that's better. All along we should be doing that. Okay. So you guys know it's above the x-axis, the complete curve, so it's going to be a positive area, right? All right. 1 to 4. Now we put x minus 2. Is that true? Why do we do that? So you could do the power rule. Is that right? Okay. So this would be x to the negative 2 plus 1 over negative 2 plus 1. From x is 1 to x is 4. So isn't this negative, is that negative 1 over x, ladies and gentlemen? Double check, is that negative 1 over x? Yeah. So we have to find f of 4 minus f of 1, and that's big F, meaning negative 1/4 minus a negative 1 over 1. So let's look at the details because we don't want to make a mistake in our arithmetic. Okay, and let's make sure that negative is there as well. So we're going to go through all that. So this is negative 1/4 now, plus 1, which is actually 1 minus 1/4 as well. If you guys remember, you could put this as 4 over 4. So the final answer is going to be what? 3 over 4 here. So this area under that curve is 3/4. That's what we just found. So sure enough, it was positive. And take a look at this. We're going to integrate from 1 to 4. So 1 is less than or equal to x, less than or equal to 4. So again, here, it looks like we got a little bit more fine with the partition here. So 1 is actually right here. And then 4 is all the way up to here. So again, area under this curve. Again, that area is going to be positive. But what do you guys notice about this here? What do you notice about this portion? What's x times, this is x times x to the 1/2. Do you guys know what that is? Isn't that x to the what? 3/2. Okay, you need to know that because you have to find the antiderivative of that, right? So from 1 to 4, x to the 3/2 dx. So x to the 3/2 plus 1 over 3/2 plus 1. And that's 2/2. 2/2. What do you guys get? Is that 5/2? So this is x to the 5/2 over 5/2. We evaluate that from x is 1 to x is 4, which is 2/5. X to the 5/2, 1 to 4, 2/5, 4/5 minus 2/5, 1/5. Now, what's nice about knowing or using the value 1 to any power will be 1. We just have to focus on, right, this portion right here. What's 4 to the 5/2? So if you remember what we did prior, right? Write this as a mixed number. Isn't that 4 to the what? 2 times 4 to the 1/2? Which is going to be 16 times the square root of 4. 16 times 2, well, that portion's 32. So we can do that. So let's write this down. 2/5 times 32 minus 2/5. And what you can now do is you can factor and say I got 2/5 times 32 minus 1, or simply 2/5 times 31. And what's 2 times 31? This is 62/5. So this is kind of the little details that you guys want to go through in terms of the arithmetic. So that's the area that's under this curve here. This is 62/5. Okay, let's see this one here. -2 and 6. So -2 would be over here. And then 6 is over here. Remember, we're looking at -2 less than or equal to x, less than or equal to positive 6. So it looks like we're going to have a couple of situations here. Above the x-axis, you do have this blue. And again, below the x-axis, we have this portion here that's red. So it looks like the blue has a greater area than the red, which means the net area will be positive. Is that right? Okay. Here we're starting to look at some more properties here. Now you could do this a couple of ways. How I do this is I focus and find the antiderivative function here for 4 minus x. Since you guys did this for homework, what is that antiderivative? What's that going to be? 4x minus 1/2 x squared. Is that true? And you evaluate that at x is -2, x is positive 6. So remember, this is the antiderivative function. So we're going to have to plug this in and perform some arithmetic. So you say we have to have here f of 6 minus f of negative 2, which will be 4 times 6 minus 6 squared over 2, and you may want to put that in parentheses, minus 4 times negative 2 minus negative 2 squared over 2. Okay, so double check here that you do have that difference. And so now you just use order of operation. So it looks like we're going to get here in the first parentheses 24 minus, isn't that 36 over 2, which is 18? Minus, this is negative 8 now, minus negative 2 squared is 4 divided by 2. Isn't that 2? So 24 minus 18, that's 6 minus a, is that negative 10? Which is 6 plus 10, which is 16. So your net area for this question is going to be 16. That's the net area. Okay. Negative 1 less than or equal to x less than or equal to positive 2. So negative 1 will be to the left here. Positive 2 is over here. So it looks like the area under the curve here is going to look like this. It's going to be positive. So negative 1 to 2, x squared plus 1 dx. Like I said, I personally find the antiderivative of x squared plus x. And what's that going to be? X cubed over 3 plus x. Right? And so now you need f of 2 minus f of negative 1. 2 cubed over 2 plus 2, put this in parentheses, minus negative 1 cubed over 3 plus a negative 1 here. So just be very careful because you can find your errors here. And now use order of operation. This is going to be, isn't that 8 over 2? Plus 2 minus, that's negative 1/3 minus 1. So we get 4 plus 2 minus, let's see what this is. Isn't that 3 over 3? Isn't that minus 4/3? So this is 6 plus 4/3. Is that right? 8 over 2 is 4. 4 plus 2. See, 2/3. That's 8 over 2, right?
8 over 3.
3 there. Oh, weird. It's kind of not too good here today. Ooh, 8 over 3. That's going to change everything here. Okay. Let's do this here. Okay. It's times 3 over 3, right? Okay. Get rid of this. Okay. Are we okay with that now? Where'd that 2 come from? That was wishful thinking. All right, let's see what we got. 8/3 plus 6/3 minus negative 4/3, right? So I'm going to keep it this way here. How about if we say 8/3 plus 6/3 plus 4/3? What does that give us? Is that 18/3? Double check. Double check. Let's double check here. Yeah, 6 and 4 make that 10. 10 plus 8, that's 18. Is that true? Double check here. So this area is about 18 thirds.
It could be 6.
Which is 6, yes. Even better. It's even better. 18 thirds, ladies and gentlemen, is what? 6. Nice. This area here is a nice 6. Good. So this is number what? 22 here. So let's do this here. So number 23, we're going to integrate from 0 to 6. So we're going to look at this vertical line for x is 0, vertical line for x is 6, and the area we're going to find is right in here. So the area is going to be negative, so we're going to expect some negative area. So the integral from 0 to 6, x to the 1/2 minus 4 dx. We need the antiderivative. So we're going to take this x to the 1/2 plus 1 over 1/2 plus 1 minus 4x. We evaluate that from x is 0 to x is 6. So don't forget, 1/2 plus 1 is going to give us x to the 3/2 over 3/2 minus 4x. And so the antiderivative really becomes 2/3 x to the 3/2 minus 4x, x is 0 to x is 6. Okay. So remember here, what we're going to have to do now is, by the fundamental theorem of calculus part 2, evaluate the antiderivatives at the values of 0 here and 6 over here. So we're going to plug in these values here. So you get 2/3 6 to the 3/2 minus 4 times 6, put this in parentheses, minus 2/3 0 to the 3/2 minus 4 times 0. And what's nice about this is when you have a 0 limit, this number is going to be 0, and that's going to be 0 because of the arithmetic. 0 to the 3/2 is 0, and 2/3 times 0 is 0. 4 times 0 is 0, and so when I subtract these zeros here, that's 0, and again, I'm subtracting another 0 over here. So really, this portion is all 0. And that's gone. So I can just drop my parentheses now, and what we end up with is 2/3, this is 6, times 6 to the 1/2 minus 24. Because your power here is 3/2. And what we're going to do is write that as a mixed number and use properties of exponents. We're really simplifying our radical. So notice what we end up with. 2 and 6 cancel, or 3 and 6 cancel there, that's 2. So our final answer is going to be the following. 4 times the square root of 6 minus 24. And that number is going to be a negative value. Don't forget we got 4 by 2 times 2. Number 24 here. Our limits are going to be from 0 to 2. So we're going to write this as 0 less than or equal to x less than or equal to 2. And that means we're going to find this area here. Vertical line through x is 0. Another vertical line to x is 2. And so the area under this curve between these two vertical lines here is what you see there. It's positive. It's going to be in blue because the curve is above the x-axis. So at this point, we're going to get to integrate. 0 to 2, 2x minus x squared dx. So we're going to use our properties, or we're going to find the antiderivative here. So this becomes 2x squared over 2 minus x cubed over 3, and we evaluate this from x is 0 to x is 2. So we'll simplify. We end up with x squared minus x cubed over 3 from 0 to 2. So this is our antiderivative function. And remember, we're going to have to evaluate this from 0 to 2, meaning f of 2 minus f of 0, again, where this is our f of x, our antiderivative function. So we're going to have to evaluate that at 2 and at 0, and don't forget we're going to subtract here. So this becomes 2 squared minus 2 cubed over 3. Since there's two terms, put this in parentheses. 0 squared minus 0 cubed over 3. And like the last problem, notice this is 0. So we just have to do arithmetic now. This is 4 minus 8/3, and we're subtracting here, unlike fractions. So I need the denominator for the first whole number to be 3, so I multiply the top by 3 and the bottom by 3. And that's going to give us 12/3 minus 8/3 for a final answer of 4/3. And sure enough, that value is positive. So this area here is going to be really positive 4/3. Number 25. Our limits are from -1 to +1. So -1 less than or equal to x less than or equal to +1. So I'm going to have to go to the left 1 to draw the vertical line through x is -1, and go to the right 1 and draw that vertical line through x is +1. And what we'll notice here is that the area under the curve here over these, I guess between these vertical lines here, it's all above the x-axis, so that area is going to be positive here. Okay. So from -1 to +1, we have 2x cubed minus 4x plus 5 dx. So we get our antiderivative here, which will be 2x to the 4th over 4 minus 4x squared over 2 plus 5x. From x is -1 to x is +1. So when we simplify this, we'll have 1/2 x to the 4th minus 2x squared plus 5x. X is -1, x is +1. So remember, we have a lower limit value, and we have an upper limit value. So we're going to evaluate this at 1 and at -1. 1, -1. And this is our antiderivative function. So we'll have 1/2 times 1 to the 4th minus 2 times 1 squared plus 5 times 1, put that in parentheses. Subtract now 1/2 times negative 1 to the 4th power minus 2 times negative 1 squared plus 5 times negative 1 here. So you plugged in the 1 value, and you plugged in here the negative 1 value. So this is going to give us some arithmetic, meaning negative 1 to the fourth power is 1, so I have 1/2. This will be minus 2. Here's what I'm saying. This is 1, this is 1, and this is 1. So we end up here with 1/2 minus 2 plus 5 minus negative 1 to the 4th power is positive 1. Negative 1 squared is positive 1. So we'll have 1/2 minus 2 minus 5 over here because we have a positive 5 times a negative 1. Okay. 1/2 plus 3 minus 1/2 minus 7. So with our arithmetic, we're going to distribute 1/2 plus 3 minus 1/2 plus 7. So notice that positive 1/2 minus 1/2 will be 0, and that leaves us with the 3 plus the 7. Final answer here is going to be 10. And there you go. So the area here is just 10. We're going to integrate from 0 to 5. X is 0. X is 5. So the area under the curve here, from 0 to 5, we see that curve is above the x-axis. That area is going to be positive here. Okay. So let's integrate 0 to 5, x to the 1/4 dx. So I take x to the 1/4 and I add 1. 1/4 plus 1, x is 0, x is 5. Now notice that 1/4 plus 1 is 4/4. And so we'll end up here with x to the 5/4 over 5/4. X is 0, x is 5, which really gives us 4/5 x to the 5/4. X is 0, x is 5, because we divide here by a fraction, which means multiply by the reciprocal. So the reciprocal of 5/4 is 4/5. We now get to plug in our limit values. Upper limit is 5. Lower limit is 0. Our antiderivative function. So f of 5 minus f of 0 by the Fundamental Theorem of Calculus Part 2. Here's our 5. Here's our 0. So we have 4/5 times 5 to the 5/4 minus 4/5 times 0 to the 5/4. And again, it's nice that we have the 0 because 0 to the 5/4 power is 0 and 4/5 times 0 is 0, meaning this portion's gone. It's just 0. What we have to notice here is that we have 5 to the 4th power here. This is a radical. It's an exponential with a rational power. So we write that as 1 1/4. So this will be 4/5 times 5 to the 1st power times 5 to the 1/4 power. And as you can see here, the 5's cancel. So you'll have 4 times the 4th root of 5. Here's our final answer. And there you go. Number 27. Our limits are from 1 to 5. So 1 less than or equal to x less than or equal to 5. So go x to 1, x is 1 here vertically. X is 5. And we're going to integrate here under this curve between these lines. And what you'll notice here is that the curve is above the x-axis, so this area is going to be positive. But I want you to note the integrand here. Because when we integrate x plus 1 over the square root of x from 1 to 5, there's really something we have to do first with this. We're going to have to use some algebra, and we're going to have to simplify. So we'll put that down here. We're going to say, use algebra, meaning distribute your division. We'll put that work over here. X plus 5 divided by the square root of x over the square root of x, plus 1 over the square root of x. Now your powers here, if we look at this, is the first power, x to the 1/2 power, and we're going to write this eventually as x to the minus 1/2 because we're going to use the power rule here with this. But we have to perform the arithmetic here. Properties of exponents beginning algebra. X to the 1 minus 1/2 plus x to the minus 1/2 gives us x to the 1/2 plus x to the minus 1/2. This is what's going to be replaced over here. So you integrate from 1 to 5, x to the 1/2 plus x to the minus 1/2 dx. We're going to use our properties of integrals. Of an integral of a sum is sum of integrals, and we're going to use the power rule here. So we have x to the 1/2 plus 1 over 1/2 plus 1 plus x to the minus 1/2 plus 1 over minus 1/2 plus 1. X is 1, x is 5. Don't forget, we're going to have to add our fractions here. So this is 2 over 2, 2 over 2, 2 over 2, 2 over 2. X to the 3/2 divided by 3/2 plus x to the negative 1/2 plus 2/2 is 1/2. And that goes from x is 1 to x is 5. So don't forget, you're dividing by a fraction, which means multiply by the reciprocal. 2/3 x to the 3/2 plus 2x to the 1/2. X is 1 and x is 5. So you're going to plug in here your lower limit and your upper limit. This is our antiderivative. We need f of 5 minus f of 1. Here's 5. Here's 1. So here's what we get. 2/3, 5 to the 3/2 plus 2, 5 to the 1/2 minus 2/3, 1 to the 3/2 plus 2, 1 to the 1/2. So notice I plugged in the limit values here for 5 and 5, and then the 1 and the 1. So let's make sure we wrote the right things here. And don't forget, in the middle here, we're subtracting again. So I'll notice that 1 of the 3/2 is 1, and 1 of the 1/2 is 1. So that's the easiest to do. And then I actually notice something here that I have the 3/2 power, so I'm going to write that as 1 1/2. And so we end up with 2/3 5 times 5 to the 1/2 plus 2 times 5 to the 1/2 minus 2/3 plus 2. And we can think there's a parenthesis here. And so we're going to have to do some arithmetic here. Notice that the 5 to the 1/2 here is just square root. So we're just going to multiply here, and we're going to get 10/3 the square root of 5 plus 2 times the square root of 5 minus 2/3 minus 2. So what we can really do here is focus on 2/3 plus 2 and get a value here. I can do the same down here if I like, but it doesn't matter. So let's take the work here or consider what we have here. 2/3 plus 2, remember we want this to be over the same denominator. So we're going to multiply by 3 and divide by 3. So this is going to give us 2/3 plus 6/3. So 2/3 plus 6/3, this is going to give us an 8/3. So what I can do is simply the following. I can write my answer as 10/3 the square root of 5 plus 2 times the square root of 5 minus 8/3. So there was some arithmetic here, and this is our final answer. Number 28. 28, if we notice, the limits are 0 to pi over 6. Now, we're going to have that vertical line going through x is 0 here. But we also want to know, where is pi over 6? Pi over 6, if we remember here, pi is approximately 3.14156. So if I approximate pi to a whole number, this is like saying this is 3 over 6, which is 0.5 or 1/2. Now, 0.5 and 1/2, if we look at this, this is 1, 2, 3, 4, 5. So every dashed line is 1. So what we're really seeing with this question is 1/2 would be right here. And so the area under that curve here is strictly positive. It's just that little portion there. I think a better question would have been from maybe 0 to pi, which is about 3. And so it would have been maybe over here. Let's undo that. 1, 2, approximately 3. And that would have been a nicer question. But then you have here an issue where you're going up there forever. So that's why they didn't put that value. They'll give you that same question in calculus 2. That would be an improper integral. Nevertheless, my point is we're going to have to find this little area there, because this is the other vertical line going through. I guess I'll put it here, x is pi over 6 here. All right, let's see what we get. So I'm going to integrate 0 to pi over 6 secant tangent. So I need the antiderivative of secant tangent. Well, that's just secant. Theta is 0. Theta is pi over 6. So this is my antiderivative function. So we're going to need to take the antiderivative evaluated at pi over 6 minus the antiderivative evaluated at 0. So this means we have, let's put every detail, we have secant of, let's go back, pi over 6, 0. So this is secant of pi over 6 minus the secant of 0. Pi over 6 is here, and 0 is here. So I would recommend people consider the reciprocal of secant, and the reciprocal of secant is actually cosine. So this is going to be 1 over cosine pi over 6 minus 1 over cosine is 0. So cosine is 0, if we remember, cosine of 0 is 1. But we need to know what cosine of pi over 6 is. So here's what we're going to look at. Let's try to draw a nicer pi over 6, I guess. And here's the detail. So if we note, and maybe we'll do that here, let's pick a nice color. You know, this dark purple is okay. So if our angle is pi over 6, let's remember, we talked about theta being pi over 6. Pi is 3.14 numerically in terms of a radian measure, but as degrees, it's 180. So this is actually going to be 180 over 6, which means we have a 30-degree angle. And so what I usually do in my life, and I encourage you guys all to do, is the same thing. Let's go back to our special triangle. And we may need to draw a bigger special triangle here. "60, 60, 60. If this is 2, this is 2, and this is 2. We have an equilateral triangle. Bisect this, and what you end up with is 2 pieces, where you have one triangle being on the left piece, if we look at that one. This length is 2. This length is bisected. It's half of 2, which is 1. And by the Pythagorean theorem, you have a right triangle. You have a right angle there. This is the square root of 3 here. That's the height of the triangle. Now this is 60 degrees, and this will be half of 60, which is 30. So this is what we want to focus on. We want to focus on that 30 degrees. And we need the cosine of 30 degrees. So at this point, remember what your definition is. Definition of cosine of an angle, okay, is adjacent over hypotenuse. So the cosine here of really 30 degrees, we need the adjacent side to 30 degrees. Now the adjacent side to 30 degrees here will be the square root of 3. Let's go back here. Maybe we should do it this way. Adjacent, and that color isn't so good. How about if we just use the blue? Adjacent, that's the adjacent side. Over the hypotenuse, that's 2. So you're using the definition here. And we're going to end up with now, I guess that was dark purple, square root of 3 over 2. But that's for cosine. Secant is the reciprocal, which is 2 over the square root of 3. And if we rationalize the denominator, multiply the top and bottom by the square root of 3, we'll end up with secant 30 degrees being 2 square root of 3 over 2. This is what we need. This is our answer that goes here. So if you're looking back at the book, final answer is going to be simply 2 square root of 3 over 3 minus 1. because don't forget you have this answer being 2 square root of 3 over 3, and you have that minus 1 over 1, which is going to be 1. So these are all the details here that you have to remember to answer, one of these kinds of questions. So that area here is what we just found. 2 square root of 3 over 3 minus 1. And it's going to be small, and it's going to be a small positive number. 29. We're going to integrate from 0 to pi over 4. 0 less than or equal to theta less than or equal to pi over 4. X is 0, and let's think about this again. Pi is approximately 3.14, but to a whole number, it's about 3. So this is going to be 3/4, which is less than 1. It's 0.75. So 1 here is all the way over here. So we have how many dash marks? 1, 2, 3, 4, 5. So each distance is about 0.2. So we have 0.2, 0.4, 0.6. This is 0.8. So right in the middle here is what we're going to look for. So if I erase some of this here, let's do it this way. This is x is 0. This is x is pi over 4. So we're going to find the area here under that curve. And it's going to be positive. Zero pi over 4 secant squared theta d theta. So we need the antiderivative of secant squared, which is tangent. So we evaluate tangent from 0 to pi over 4. So remember, this is our antiderivative. So we need f of pi over 4 minus f of 0. 0 here, pi over 4 over here. So you're going to get tangent of pi over 4 minus tangent of 0. Now, tangent of 0 here is 0. And we need to know what tangent of pi over 4 is. So if you go back here, and we try to find pi over 4, you're going to go to another special triangle, which is your 45, 45, all right, 90-degree triangle here. One, square root of 2. Here's 45 degrees here, so we may need a bigger triangle. 1, square root of 2, pi over 4. So your definition of tangent of any angle is going to be opposite over adjacent. So again, we need the opposite, which is here. We need the adjacent, which is here. So tangent here of 45 will be one over 1, which is just 1. So this answer is 1. So now 1 minus 0 will be 1. So the area under this curve here is the value 1. number 30. Our limits go from pi over 4 to 3 pi over 4. Now pi over 4 again we've seen is about 0.75. So every distance here is 1, 2, 3, and 4. So it's going to be again, 1 would be here. This is a half. So looks like we're right through the intercept here. This is pi over 4 here. And then 3 pi over 4 is about 0.75. And let's be careful here. These are positive values, not negative values. Okay. So let's go back. Pi over 4 will be about, again, 0.75 numerically. 3 pi over 4 now, you remember, pi we're going to assume to be around 3, so it's 9/4, that's 2 1/4. Or simply 2 and 0.25 here. So let's see where that would be now. It looks like here this is 1. This is 0.51, 1.52, and this might be something over here. Maybe it's over here. We'll see. So this is x is 3 pi over 4. Now pi over 4 again is about 0.75. So, and it's actually a little bit bigger. So this is 1/2, and it looks like these are actually intercepts. So that's pretty good. We can double check, but that's what it looks like to us here. Okay, the area is above the x-axis, so it looks like we're going to have positive area here. All right, that looks like kind of what they want us to do here. So when we integrate from pi over 4 to 3 pi over 4, 2 minus cosecant squared x dx, we need the antiderivative. Now the antiderivative of the first function here, 2, is going to be 2x minus. We need the antiderivative function now for cosecant squared. Now remember, the derivative of sine is cosine. The derivative of cosine is minus sine. The derivative of secant is secant tangent. Okay? So if we go back and think about what this might be, what's the derivative of tangent? Secant squared. So the derivative of cotangent is actually, let's note here. Let's write that down. The derivative of cotangent is minus cosecant squared. So that means the antiderivative of minus cosecant squared will be right here, cotangent. And we already have here the negative sign, so be careful here. If you see, let's erase this here, that negative cosecant, this is negative cosecant, the antiderivative is simply going to be cotangent, and that's plus, because you're already accounting for the negative sign here. Okay. Evaluate from x is pi over 4 to x is 3 pi over 4. So here's my antiderivative function. We're going to plug those values in. So we're going to find f of 3 pi over 4 minus f of pi over 4. So that's going to be 2 times 3 pi over 4 plus cotangent of 3 pi over 4 minus 2 times pi over 4 plus cotangent of pi over 4. So double check here to make sure we did everything okay. Pi over 4 is that lower limit. The upper limit is 3 pi over 4, so we have to put the 3 pi over 4. Here it is. Here it is. Pi over 4, pi over 4. There's our lower limit. So we just have to find some values here, but before that, let's do some arithmetic. Let's notice at 2 and 4, we end up with 3 pi over 2 plus cotangent 3 pi over 4 minus pi over 2, and let's distribute, minus cotangent of pi over 4. We're going to distribute this negative sign. So we're going to have to note what cotangent 3 pi over 4 is and tangent, or let's go back, cotangent 3 pi over 4 and cotangent pi over 4. So if you remember what we did in the last problem, or one that we did very similarly, we know that tangent pi over 4 is 1, so 1 over 1 is 1. We have the reciprocal identity. And I want to mention something here that's very useful. You see, we have to find the value here of cotangent 3 pi over 4. Right here. I'm going to think of this as 1 over tangent of 3 pi over 4 personally. And I remember that pi over 4 is in quadrant 1. So if I go and rotate my ray counterclockwise, I got 1 pi over 4. The ray over here now is 2 pi over 4. Let's get our computer back. And then I have another ray, if I rotate another pi over 4, which is 3 pi over 4. And so this is a quadrant 2 angle. We got quadrant 3, we got quadrant 4. So I'm going to ask you to all remember that all students take calculus. Now, what that identifies is the trig functions where you have positive values. So in quadrant 2, only sine is positive. That implies that cosine's negative and tangent's negative. And so if you remember from trigonometry, that means tangent of 3 pi over 4 is negative because the reference angle of tangent being pi over 4, way over here, we know tangent is positive 1. That's our reference angle. But in quadrant 2, that now means that this angle, 3 pi over 4, is negative because all students take calculus, and that really implies that my tangent here is negative in quadrant 2. So what we have here as an answer will look like this. Let's put this together. We know 1 over negative 1 means this is negative 1. So we'll have 3 pi over 2 minus 1 minus pi over 2 minus 1. And by our arithmetic, by combining like terms, 3 pi over 2 minus pi over 2 is 2 pi over 2. This will be pi. We're going to combine this first term, and then we get pi minus 2, and the next term. So the area under this curve here is really pi minus 2. And remember, pi is about 3.14, so 3.14 minus 2 is in fact a positive number. But this is all the details that you go into integrating. 31. We have a nice piecewise function. It's absolute value. But the limits here are from -1 to 3. So let's see where that looks like. That's to the left, negative 1. And then 3 would go 1, 2, and 3. So our area under our curve now here, we have this triangle here and this portion here. So notice a very special point at 2 here. So it looks like we're going to have two integrals here, one on the left, one on the right, because we have to look at this absolute value curve as a piecewise curve. Now remember, the absolute value of x minus 2, we define this piecewise as x minus 2 when x minus 2 is greater than 0, and opposite x minus 2 when x minus 2 is less than 0. So if we simplify a little bit here, here's the definition of our function. It's x minus 2 when x is greater than or equal to 2, and it's going to be minus x plus 2, or we can write this as 2 minus x when x is less than 2. Now what we did here is we simply solved these two simple inequalities by actually adding 2 to both sides here. So you add 2 to the left, 2 to the right for both of these. And now you get your new limits. And let's actually change some of these colors here. So we can look at this a little bit more clearly. This is the top portion, which is right here. These are values of x that are greater than or equal to 2. Those values of x are down here. They're to the right here. Okay, we're saying use this curve here for those values of x, greater than or equal to 2. We're also saying over here, right, for values of x that are less than 2, all these values of x here, use this left portion of the curve. This is why we say we have piecewise functions. They're defined in pieces. So the left is here, the right is here. We have two pieces. This is how we have to integrate. Don't forget this very special point 2 here. So as we've seen in class, we're going to separate this into two integrals. Meaning, if I integrate from 1 to 3, the absolute value, x minus 2 dx, the left integral will be from negative 1 to 0. Because this is where negative 1 is. Right down here. And this, if you want to draw a vertical line here, you can. It's not necessary. This is where x is 2. This is my first integral. That's the left portion here. So I'll put this even in green here. So we have 2 minus x here dx. So let's put it all in green. Maybe we can see it better. Negative 1 is 0. Plus, now we're going to put this other one, I guess that was in black. We're going to integrate now. From 2 to 1. And that curve here was x minus 2 dx. Actually, from 2, no, let's go back. Oh, we made a mistake. This is 0, 2. We're focusing too much on the color. So this is negative 1 to 2. Right, from here to here, and this will be from 2 now to 3 here. So let's really fix that. Okay, now we're good. Okay, because this is where 3 is. This is where 2 is as well. So now I have the appropriate integrals here. And there's 2. So I'm going to find a left area and a right area. So let's do this work in green here since we have 2 to do. the antiderivative of 2 minus x is 2x minus x squared over 2. That's from negative 1 to 2. Plus, let's write it that way. Antiderivative of x minus 2 will be x squared minus 2 minus 2x. And that's from 2 to 3. Okay, let's plug these values in now, because we have to find f of 2 minus f of negative 1, and also f of 3 minus f of 2. So here's what you get. 2 times 2 minus 2 squared over 2 in green, minus 2 times negative 1 minus negative 1 squared over 2. Don't forget, we need to add this with, in blue, or now black, 3 squared over 2 minus 2 times 3 minus 2 squared over 2 minus 2 times 2. So double check these limits here. Upper limit is in purple. Plug in 2, plug in 2. Upper limit here in purple, 3. You're going to plug in 3, plug in 3. Lower limit is in red. So for the green integral, negative 1 is here and here. For the black integral, lower limit is 2 here and there. Okay. 4 minus 2. This is my first parentheses. Minus negative 2 minus 1/2. Plus 9 halves minus 6 here, minus 2 squared is 4. 4 divided by 2 is, this is 2, minus 4. This is the next portion here. So we're just going to simplify very carefully here. This is 2, because 4 minus 2 will be 2. Minus, this is negative 2 minus 1/2. Don't forget, multiply by 2, divide by 2. It's negative 4 minus 1. Looks like it's negative 5/2 here. Plus times 2 divided by 2. So we have 9 halves minus 12 halves. Well, that's negative 3 halves. Minus 2 minus 4 is negative 2. So we get 2 plus 5 halves here, plus negative 3 halves plus 2 times 2 over 2. And over here, we're going to add these fractions as well. 2 over 2. So let's see what we get. 4 halves plus 5 halves plus negative 3 halves plus 4 halves here. Nine halves plus negative 3 halves plus 4 halves, that's 1/2. Final answer is going to be simply what? 10 halves, or the value is 5. So you're going to have to do this arithmetic here. So this is the total area. I didn't separate them and get the individual values. If I did, let's note that in green here, we can think of it this way. 9/2. This will be the left portion here. This is 9/2. One half. This portion's 1/2. So 9/2 plus 1/2 is 10/2, better known as 5. So this is how we integrate a piecewise function. (32) -1 to 3. -1 less than or equal to x less than or equal to 3. X is -1. 1, 2, 3 here. So we're going to look at the area under this curve here. And we notice that it's all above the x-axis, so that area is going to be positive. And again, we notice this very special location here, the origin. So we're going to have two integrals. So because we notice that we have a piecewise situation. This is piecewise. 4 minus the absolute value of x, this is how we define this. 4 minus x, when x is greater than or equal to 0. 4 minus the opposite, when x is less than 0. And so we define this as 4 minus x, x is greater than or equal to 0, or 4 plus x, when x is less than 0. So again, we have two pieces here. The top piece, 4 minus x for positive x. So all these x values that are positive, including 0, we use this portion of the graph. That's 4 minus x. And I think I'm going to change this color and say for 4 plus x, for the negative values are to the left of 0. This is the graph we use. So we're going to have two integrals again. And let's set this up. I'm going to do the left portion first, and that's in dark purple. So notice we're going to integrate from -1 to 0 here. So I want to start completely from the beginning to say the following. From -1 to 3, 4 minus the absolute value of x dx is defined in pieces. -1 to 0. We use 4 plus x dx. Plus, now the green piece. We go from 0 to 3. And that's going to be 4 minus x dx. Okay. So let's find our antiderivatives here. So I need this antiderivative, which will be 4x plus x squared over 2. We evaluate that from -1 to 0. Plus, now we have the second antiderivative, which will be 4x minus x squared over 2, evaluated from 0 to 3. So we're going to plug everything in here. So remember, f of 0 minus f of -1. And here we have f of 3 minus f of 0. we're going to add those. Okay. In purple, 4 times 0 plus 0 squared over 2 minus 4 times negative 1 plus negative 1 squared over 2. Because remember, we have a upper limit, which is here, and a lower limit, which is here. And in the green, you can say plus. We'll have 4 times 3 minus 3 squared over 2 minus 4 times 0 minus 0 squared over 2. Because again, we have the upper limit of 3, which goes here and here, and the lower limit of 0, which goes here and here. Okay. I want to point out a couple of nice situations. Because we have 0, that's 0. Because I have zeros here, this is 0. So this is kind of nice. Let's look at the purple situation now. We got minus negative 4 plus 1/2. And then in green here, plus 12 minus 9/2. So we looked at what was left here. And maybe it'd be best to just simply, let's just distribute here. You got 4 minus 1/2. Let's go back and put this plus in blue. And then in green, you have the following here. 12 minus 9/2. So we can combine like terms here. And here's what I mean by combining like terms. It looks like we have 4 and 12 gives us 16. And then we have minus 1/2 minus 9/2. Well, that's minus 10/2. Or simply 16 minus 5, which is actually going to be now 11. So the total area under the curve here is the value 11. So I can say this whole thing is 11. But if you were interested in some of the other details, meaning that what is 4 minus 1/2? What's the left portion, I believe? If that was purple, that's on the left, yes. The left portion, well, 4 minus 1/2 is 8/2 minus 1/2. And that's going to be 7/2. That's for the left portion. This portion over here is 7/2. It's to the left of that 0. On the right side in green, what we can do now is just simply compute 12 minus 9/2. Now, 12 is really 24/2. So 24 minus 9, right? 24/2 minus 9/2 is going to be 15/2. All right, so let's note this in green. (24 minus 9/2) is 15/2. Now something's wrong here. Let me be careful here. 4, that's 8. Okay, let's double check. 15 halves, 22 halves. It looks like we're good. No, that's 15 halves. I apologize. Let's find the right color. So this portion is 15 halves. This is what we found here. This is for the right portion, and here is for the left portion. And if you add those, remember 7 halves plus 15 halves is 22 halves, which does give you 11. And this is how we integrate here, piecewise functions. Okay. Number 33. 0 to pi. 0 less than or equal to theta, less than or equal to pi. So pi, remember, is about 3.14, and we know where 0 is, so I have this 0. This is the line, theta is 0, and about 3. We got 1, 2, 3, and a little bit more than 3. We're looking for area under this curve here. So that area there under that curve is positive because the curve is above the x-axis. So let's see what we get now. 0 to pi, theta minus sine theta, plus 2 cosine theta, d theta. So by properties, of integrals, we can look at each one individually, or we can actually just simply find the antiderivative of each one. So by now, you guys should be able to do that because you had homework on antiderivatives. So this function is going to be theta squared over 2 minus. The derivative of sine is cosine. Derivative of cosine is minus sine. So this would be minus cosine. Let's think about that again. We need the antiderivative of sine. Yes. Plus 2 times the antiderivative of cosine. And that's just going to be sine. Theta is 0, and theta is pi. So theta squared over 2 plus cosine of theta plus 2 sine theta from 0 to pi. This is my antiderivative function. So we get f of pi minus f of 0. Let's plug in these values. Pi squared over 2 plus cosine pi plus 2 sine pi minus 0 squared over 2 plus cosine 0 plus 2 sine 0. So don't remember, or don't forget. Let's double check to see if we applied the limits correctly. This is my upper limit. Okay, and then we have to check the lower limit. 0, 0, 0. And then we actually find some nice values here. So this is kind of nice. If we look at the cosine function, cosine of pi is -1, while sine of pi is 0. Cosine of 0 is 1, and sine of 0 is 0. You want to consider your curves, your sine and cosine curves, so you guys can actually find these values pretty quickly. So remember, sine of pi is 0 and sine of 0 is 0. For cosine, cosine of 0 is 1, but at pi it's -1. So we're okay. So let's put this together here. We get pi squared over 2 minus 1 because we add a negative, and then we have a 0. So here's my first parentheses. And then I have, let's look at these details here. This is also 0. So I have a minus 1 here. So if we remove our parentheses, we get pi squared over 2 minus 1 minus another 1, which gives us pi squared over 2 minus 2. Pi is about 3.14 or 3, so we get 9/2 minus 2. That's 2.5 minus 2, so yes, this area is positive. Pi squared minus 2. That's the area under that curve. (34) 0 to 2 pi. So we're going to integrate here. Or let's look at the limits first. When you say 2 pi, that's about 6. So theta here is going to be the 0. Got this vertical line. 6 is about over here. That's a little bit more, so you guys know. So that's about where 2 pi would be. So let's take a look at this kind of situation here. In blue, we're above the x-axis. In red, we are below the x-axis. So as you guys can see, that red area outweighs the blue area. There's more red space there than blue, so this answer is going to be negative overall. So we need some antiderivatives here. And don't forget, looks like there's a typo. This needs to be a d theta here. Okay, the antiderivative of cosine is sine. The antiderivative of 1 is theta. So this is my antiderivative function. So we have f of 2 pi minus f of 0. This is my upper limit of 2 pi. There we go. And we also have our lower limit of 0 over here. Here's what we get. Sine 2 pi minus 2 pi minus sine of 0 minus 0. 2 pi, 2 pi, 0, 0. Sine of 2 pi is 0. Sine of 0 is 0. So it looks like we're left with here negative 2 pi minus, and we should actually just notate this as well and say this whole thing is 0. So 2 pi minus 0 is going to ultimately be simply negative 2 pi. And let's put that answer in black here. So sure enough, we get a negative answer, negative 2 pi, which means that net area in total here, the net, is negative 2 pi. We didn't compute the blue area separate from the red area. We computed all of this at the same time, meaning we went from 0 to 2 pi. We did not do this piecewise. This is why it's the net area. Number 35. 0 to 2. Let's compute this. This is x to the 4th over 4 minus 2x cubed over 3 plus x squared over 2 minus 4x. This is my antiderivative function. So let's remember here, since x is 0, here's my 0 axis, or my vertical line, and then x is 2 here. So let's remember an important detail, that the area here between 0 and 2 is below the x-axis, so this final answer is going to be negative here for this integral. So let's see what this is, because we already integrated. So I have my antiderivative function here, and that's not theta anymore. That was the last question, or a few questions back. That's theta. That's going to be x. Let's plug in both the upper limit value of x is 2 and the lower limit value of x is 0. So we'll get f of 2 minus f of 0. So there's going to be some arithmetic here. This is 2 to the 4th over 4 minus 2 times 2 cubed over 3 plus 2 squared over 2 minus 4 times 2 minus 0 to the 4th over 4 minus 2 times 0 cubed over 3 plus 0 squared over 2 minus 4 times 0. So again here, upper limit value, I think it's this purple here, was 2 that we plugged in. Okay, there's the 2. And let's double check the lower limit value, 0, 0, 0, and 0. So we have some arithmetic to do. First parentheses, 2 to the 4th power. That's 16 over 4 minus really another 2 to the 4th power, which is 16 over 3, plus 4 over 2 minus 8. That's in our first parentheses. And notice what we get that's really nice. This whole thing is 0. Because 0 to the 4th is 0, 0 cubed is 0, 0 squared is 0, and 4 times that number 0 is 0. The whole thing there is 0. So what I have really is, if I do some more arithmetic, 4 minus 16 thirds plus 2 minus 8. Let's combine our terms here. 4 minus 2 is 2. 2 minus 8 is, this is negative 6 minus 16 thirds. So what I'll have to do here is multiply the top by 3, divide by the bottom by 3. So this is negative 18 thirds minus 16 thirds, and that's going to give us, as a final answer, negative 34 thirds. Because negative 18 minus 16 is negative 34. So sure enough, the answer is negative. So your area here is negative 34 thirds. And, you know, I guess we can make sure that negative sign is clearly away from the number. But it's a negative 34 thirds. That area is below the x-axis. The last question. Number 36. We're going to integrate from negative 5 to positive 5. And so if we take a look, all the area under this curve is positive. So if you take a closer look here, I have a piecewise function. So I'm going to have to remember what this really is. So I'm going to do some work here to say, here's my function. Let's call this f. And so f of x here is 2 absolute value x minus 1 plus 3. So I'm going to have to use my definition of piecewise for the absolute value of x minus 1. So here's what we get. 2 times x minus 1 plus 3 for x minus 1 is greater than 0. 2 times, let's put this way, negative x minus 1, it's the opposite. And that happens when x minus 1 is less than 0, and that's strictly less than. So we're going to have to do some cleaning up here. 2x minus 2 plus 3, when x is greater than or equal to 1, and we have negative 2x plus 2 plus 3 when x is less than 1. So I'm just simplifying these expressions here. And to the right here, we add 1, and we get these new limits. So here's what we get. Two x plus 1 for x greater than or equal to 1, negative 2x plus 5 for x less than 1. So this is what we're going to have to integrate. So notice here, this is all about where x is 1 here. So let's look at the portion again. We'll say this is in green here. For the values of x that are less than 1, we use the left portion of the curve. For values of x that are greater than 1, we use the right portion of the curve. So let's set up these integrals here. Originally, you're integrating from negative 5 of that function, and to the left here in green here, we go from negative 5 to positive 1, and that to the left there is the function negative 2x plus 5. So we have negative 2x plus 5. Plus, in purple, 1 to 5. And we're going to deal with the right portion here. 2x plus 1. So these are the integrals we have to perform here. Okay, so let's do this work in green here. So we have to go from negative 5 to 1, negative 2x plus 5 dx, which is negative 2x squared over 2 plus 5x. X is negative 5 to 1. So we'll get negative x squared plus 5x. X is negative 5 to x is 1. So this will be f of 1 minus f of negative 5. So we get negative 1 squared plus 5 times 1 minus negative 5 squared plus 5 times negative 5. Make sure you applied your upper limit value and then your lower limit value here. Okay. So by the arithmetic, we'll get negative 1 squared will be negative 1 plus 5 minus negative 25 minus 25. So we'll get 4 minus negative 50, or 4 plus 50, which is 54. So the left portion in green, this is 54. The purple portion, from 1 to 5, 2x plus 1. This is going to be 2x squared over 2 plus x evaluated from 1 to 5, which is really x squared plus x from 1 to 5. This is my antiderivative function. F of 5 minus f of 1. So we plug in 5 squared plus 5 minus 1 squared plus 1. 25 plus 5 in the first portion. 1 squared is 1, and 1 plus 1 makes that a 2. So we get really 30 minus 2, which is 28. So the right side over here, the area is 28. So your final answer here is going to be, if we look at this integral, we say, okay, you were 54. And over here, you're 28. So when I add these values, 54 plus 28 is 82. So the total area here is 82, and how you have to integrate this is by using piecewise functions, or the concept of a piecewise function. And you know that when you have the absolute value. The absolute value is right there.